Jai Shri Gurudev. Dear students, welcome to today's session. Today I'll be teaching you about an important concept in the first module named as analogous systems. Analogous systems are nothing but what? A system which is similar to a given system. That is what analogy means. So here we are trying to convert a mechanical system into an electrical form using two types of analogy which are termed as force voltage analogy and force current analogy. So here we are considering an example of a translational system. So in terms of translational system, if I consider my analogy, I can call this analogy as force voltage analogy. If I'm talking with respect to rotational system, then it is termed as torque voltage analogy. So there is a table given here in the presentation. Please do note down. So here in the first column I have listed the important translational elements and the corresponding values. Here in the second column a list of rotational elements is given, and in the third column the analogous electrical values are given. So when I consider my translational system, force is considered to be equivalent to voltage. So this force is taken as equal to voltage. So that analogy is therefore termed as force voltage analogy. And mass is considered as equivalent to inductance, and damper D is considered as equivalent to resistance. Spring constant K is considered as equivalent to reciprocal of capacitance, which is termed as elastance. And displacement x is considered as equivalent to charge q, and velocity is considered to be equivalent to the current value I. So you need to remember this. And if I consider a rotational system, torque is considered as equivalent to voltage, and this analogy is termed as torque voltage analogy. Inertia J is considered as equivalent to inductance L, and damper D is considered as equivalent to resistance. And spring here again is taken as elastance, which is 1 by C, and displacement theta is considered as equivalent to charge Q, and velocity is considered as equivalent to current. The table showing the analogous system using FI analogy. So here in the first column translational elements are given, in the second column rotational elements are given, followed by electrical elements in FI analogy form. So in case of translational system, force is considered to be equivalent to current. That is why it is termed as force current analogy, which is shortly termed as FI analogy. And mass is considered as equivalent to capacitance. Damper coefficient D or B is considered as equal to conductance, which is represented as 1 by R, and the spring coefficient K is considered as equivalent to reciprocal of inductance, that is 1 by L, and displacement X is considered as equivalent to flux, and velocity is considered as equivalent to voltage. With respect to rotational system, torque is considered as equivalent to current, inertia J is considered as equivalent to capacitance, damper D is considered as equivalent to conductance, and spring coefficient K is considered as equal to reciprocal of inductance. Displacement, angular displacement theta is taken as flux, and angular velocity is considered to be equivalent to voltage. So this is the consolidated table showing you the relationship between translational system, rotational system, and electrical system using FI analogy. So this table is useful to solve many of the problems which will be given to you. Now this is an example which I am taking to show you the force voltage and force current analogy. So as you can see here, we have mass M1 and M2, So mass m1 is connected to a fixed wall through a spring k1, and m1 is connected to m2 using a dashpot with friction as b and spring with the coefficient as k, and force F of t is applied for mass m2. So because of movement of this m1 and m2 masses, we have a friction here which is represented as b1 and b2. So coming to the displacement, due to this applied force, we have a resultant displacement which is existing in the system, which I am representing it as x and x1. Let's now see the free body diagram for the given problem. So for mass m1, the applied forces are represented as m1 dx1 by dt, k1x, b1x, b into x minus x1, k into x minus x1. And for mass m2, we have the force due to the elements which are connected to m2 as b into x minus x1, m2x, b2x, k into x minus x1. The applied force here is represented as F of t. And the equations for balancing the forces on m1 and m2 are represented here. So this is for the node x, wherein force F of t is taken as equal to m2 d square x by dt square, which is represented as x double dash, b2 x dash, which is nothing but equal to dx by dt, plus b into x dash, that is dx by dt, minus x1 dash, that is dx1 by dt, plus k into x minus x1. So these are the elements which are connected to your mass m2. And similarly here with respect to mass m1, it is taken as m1 d square x1 by dt square plus b1 dx1 by dt plus k1 x1 is equal to b into dx by dt minus d x1 by dt plus k into x minus x1. So when I move these two towards my left hand side, here you can equate it to 0, and this could be taken as x1 minus x and x1 dash minus x dash and x1 minus x. That is also applicable. Now by applying the Laplace transform for these two equations, we can write the same equation as m2s square plus b2s plus bs plus k into x of s minus bs plus k into x1 of s as equal to f of s. We have taken the Laplace transform for the first equation, and I am combining the terms x of s and x1 of s, which is equated to f of s. Similarly, for the second equation, when we apply the Laplace transform, it is taken as m1s square plus b1s plus bs plus k plus k1 x1 of s is equal to bs plus k x of s. Now by rearranging the terms and solving for x1 of s, you will get an expression like this. Okay. Now finally the transfer function g of s is taken as x of s by f of s, which is nothing but equal to m1 s square plus b1s plus bs plus k plus k1 divided by m2s square plus b2s plus bs plus k into m1s square plus b1s plus bs plus k plus k1 minus bs plus k whole square. Now, this is the transfer function what we have got for the system. Now if we apply the force voltage analogy for the two equations which we have developed, right? So we will be getting the equation as m2 is replaced with L2, and here the velocity is replaced with current I. So it is taken as L2 di by dt plus R2I plus Ri minus I1. Here B is replaced with R and K is replaced with C. So it is 1 by C integral of I minus I1 dt, because we have taken the force as equal to K into x minus x1. So but here current is considered as equivalent to velocity. So if we express displacement in terms of velocity, is taken as integration. So 1 by c integration of I minus I1 dt is nothing but equal to the voltage E of t. Similarly, for the second equation, if we apply Fi analogy, it is represented as L1 di1 by dt plus R1 I1 plus 1 by C1 integral of I1 of t dt is equal to R into I minus I1 plus 1 by C integral of I minus I1 dt. Now, using these two equations, we will try to write the electrical network in the mesh form. So, here whatever elements which are experiencing only the displacement x1 should come here, and the elements which are experiencing both the displacement should be connected in a parallel form like this. So in the first mesh we have the elements as C1, L1, R, that is according to the second equation, and since we have I minus I1 with respect to C and R, that is connected here, and R2 and L2 are connected here along with the voltage E of t. So the equivalent values of the physical systems are represented here. So L2 is nothing but equal to M2, R2 is equal to B2, C is taken as K, R1 is taken as B1, L1 is represented with M1, C1 is taken as equal to K1, and the current I is taken as equal to nothing but the derivative of the displacement x and x1. E of t is taken as equal to force and R is taken as equal to B. So these are the equivalent values what we have got with respect to force voltage analogy. Now let's take one more example. So here one mechanical system is given for which you need to write the analogous circuits. We have three masses M1, M2 and M3, and we have a spring K1, K2, K3 and K4 and dashpot B1 and B2. So here the wheel indicates that it is frictionless, so we are not considering any friction. So marking the direction of the displacement in the direction of the applied force, we have three displacements, that is x1, x2 and x3. Now we shall draw the analogous circuit for this particular mechanical system. Now here we have three displacement, that means that it is represented with three nodes x1, x2 and x3. So force F of t is applied for mass m1, so that is connected here to node x1. We have mass m1, k1 and b1, that is connected to displacement x1, and k2 is appearing between x1 and x2, so which is connected here. And for the node x2 we have m2, k3 and b2 which are experiencing only the displacement x2, and k4 is experiencing the displacement x2 and x3, and m3 is experiencing only the displacement x3. So this is the mechanical network which we have drawn for the system given to us by considering the forces acting on the masses m1, m2 and m3 respectively. Now coming to the equations, at node x1 we have f of t applied force as equal to m1 d square x1 by dt square b dx1 by dt plus k1 x1 plus k2 x1 minus x2, and at node x2 we have the values as k2 x1 minus k2 x2 is equal to m2 x2 double dash, that is d square x2 by dt square plus b2 dx2 by dt plus k3 x2 plus k4 x2 minus k4 x3. And similarly the third equation is m2 x2 double dash plus b2 x2 dash plus k1 k2 k4 into x2 minus k3 x1 minus k4 x3 equal to 0. Now here as an example I have taken force current analogy. So here by replacing the corresponding elements, force is replaced with current I, m1 is replaced with c1, and here the acceleration or the velocity is replaced with the voltage v. So v1 by r1, 1 by l integral of v1 dt plus 1 by l3 integral of v2 dt. The corresponding values are given here, minus 1 by L3 integral of V2 dt. Similarly for the second equation we have applied the analogy and we are able to get this particular equation, that is C2 dV2 by dt plus V2 by R2, 1 by L1 plus 1 by L3 plus 1 by L4 integral of V2 dt minus 1 by L4 V3 dt minus 1 by L2 V1 dt. And similarly for the next equation we have C3 dV3 by dt plus 1 by L4 integral of V3 dt minus 1 by L4 V2 dt is equal to 0. So these are the force current equations using the analogy. Now this is the network what we have drawn for the given mechanical system. So the network almost looks similar to the mechanical network what we have previously drawn. Only thing is here we have replaced mass with C, spring with 1 by R, and dashpot value that is spring with 1 by L1 and dashpot with 1 by R. Okay, so replace the corresponding elements, and this is the electrical equivalent network what we have for the given mechanical system. I hope you have followed this analogous systems example. So this is one more example wherein we have a spring, a dashpot, and mass m1 and m2 which is connected in between like this. So this is the mechanical network what we have. So two displacements x1 and x2, m1 is connected here, k1 is connected here, b, and k2 is coming in between these two nodes, and m2 is connected to displacement x2. And the equations at node x is f of t is equal to m1 d square x1 by dt square plus b x1 plus k1 x1 plus k2 x1 minus x2. And for node x2 it is k2 into x1 minus x2 is equal to m2 d square x2 by dt square. So by applying the Laplace transform we will be getting two equations like this. And now this is the equivalent force voltage analogous circuit and the equation. So exactly the same procedure you need to follow. So convert the corresponding elements using the analogy, and since we have two equations, we are going to have two loops here with the currents as I1 and I2, and the elements are R, L1 and C1 here in the first loop. C2, since it is experiencing two displacement or two currents, it is connected parallelly like this, and here M2 is replaced with L2. So similarly, few more examples are shown here wherein you're asked to find out the transfer function for this particular mechanical system. The same procedure should be followed. First write your equations, convert it into Laplace transform, then solve the equations for the given value. So it is x1 of f of s is taken as this particular transfer function, and x2 of s by f of s is taken as equal to this. Okay, now coming to the rotational system. So this is an example of a rotational system. Now we'll try to analyze this rotational system using the two types of analogy, that is torque voltage analogy and torque current analogy. So here I have a inertia element J1 and J2, a spring and a dashpot which is connected to a fixed wall. So due to the applied torque we have an angular displacement which is represented here as equal to theta. Okay, so here output is displacement, input is torque, so transfer function is taken as theta of s by torque t. Now for this particular system, if we consider the angular displacement, so I have here J1 which is experiencing the torque T1. So for this particular inertia element J1, the equation is J1 d square theta 1 by dt square plus k into theta 1 minus theta is equal to t. So this is the equation, and when we apply the Laplace transform and simplify, we are going to get the value as J1 s square plus k plus into theta 1 s minus k theta of s is equal to t of s. So this is one equation for J1. Similarly for J2, if we write the equation, it is J2 d square theta by dt square plus b d theta by dt plus k into theta minus t. Theta 1 is equal to 0 because torque is applied only for J1, not for J2. And after taking Laplace transform for this, you are going to get the equation as J2 s square plus bs plus k into theta of s minus k1 theta 1 of s is equal to 0. Or after simplification we can get the theta 1 value as equal to j2 s square plus bs plus k divided by k into theta of s. Now when we simplify these two equations, we will be getting the transfer function as equal to theta s by t of s is equal to k divided by j1 s square plus k into j2 s square plus bs plus k minus k square. So this is the transfer function what we have got for the rotational system which is given to us. So I hope today's session was interesting. Thank you all. So in today's session we have discussed about problems on translational systems and how these translation systems can be converted into an electrical form using the two types of analogy, that is torque voltage analogy and force voltage analogy and force current analogy. And similarly for the rotational system we have two analogy, that is torque current analogy and torque voltage analogy. So thank you all for your patience listening. Have a nice day.